Welcome back to UBC CS 532W, the second to last lecture. And today we have Will Harvey, a PhD student in the Play group, who will give a lecture on reparameterization and normalizing flows. Please, as usual, ask questions and give Will a hard time. I don't know. Have you actually taught before yet, Will? Did you do tutorials at Oxford or?
No, this is my first time. So yes.
All right. So this is it's game time. So give him as you would a substitute teacher a good old hard time. Take it away.
All right. So we will be talking today about reparameterization and normalizing flows, as Frank has already said. But so we'll start with one little slide of background on the change of variables rule, since we will then use this repeatedly throughout. And then we'll talk about reparameterization, which I think Frank has already covered in this course a few lectures ago, but we'll do a slightly different perspective. And then we will move on to normalizing flows for the rest of the lecture. Okay, so first off, with our background on the change of variables rule. So essentially, the change of variables tells us if we have one variable x0, which we know is distributed according to some base distribution, which here we're calling u. The change of variable rule tells us if we then transform x0 using some function f into another variable, which here we're calling x, then the change variables rule tells us what is the probability density function for x, given this function f and the base distribution u. And so there's a couple of conditions that we need for this to be well defined. So one is that the transformation that we use, f, is going to be invertible or bijective. And the other is that the mapping is continuously differentiable in that it has a continuous derivative. Okay, and then if those are satisfied, we can use this equation down here. So the probability density over x is equal to the density u over x0 times this guy. And so since this is meant to be just a function of x, we should note that we can get x0 given x, since we said that f was invertible. So if we invert f and just feed through x, we can get out x0, plug that into here. And then this term is the determinant of the Jacobian of f evaluated at x0. And so first, let's just go over what the Jacobian is. So the Jacobian is like this generalization of the derivative to higher dimensions. So it's basically a matrix where we have in row I and column j, then we have the derivative of the ith dimension of the output with respect to the jth dimension of the input. And then, yeah, we have that for every row and column. And this is a square matrix, since f has the same number of output dimensions as input dimensions. And so we can compute its determinant up here and the absolute value of the determinant and invert that. And that is how we get the probability density of x. All right, so moving on now. We are now going to start to look at reparameterization. And so this is just a sort of motivation for why we want to do the reparameterization trick. And so we're looking at problems where we need to compute a gradient that looks like this. So a gradient of an expectation. So the gradient with respect to theta, the expectation over p of x of some function h, which can be a function of both x and theta in the most general case. So first, we're going to sort of look at the slightly easier scenario where p of x does not depend on theta. So if this is the case, then we can do this bit of maths that we're coming to. So we can just write out the expectation in terms of an integral, the integral of p of x times h. So that's, I think, fairly straightforward. And then we get to the slightly more interesting step of we want to move this gradient with respect to theta inside the integral. So this is something that we can't actually always do in general, and we're going to come back in a few slides' time to when exactly we can swap the integral and the derivative. But for now, we're just going to assume that h is sort of sufficiently nice and differentiable that we're allowed to do this. And then since p of x doesn't depend on theta, we can just sort of slide this derivative inside here. And so we end up essentially with an expectation over p of x of the gradient with respect to theta of h. And so this now is something that looks slightly nicer to estimate than the thing we started with at the top here, because we've got the expectation on the outside. And so we can estimate this with Monte Carlo samples of x. So we can just sample x from p of x and then compute this term on the inside. And we might be able to compute the inside term with, for example, automatic differentiation. And then we can just take lots of samples of x and average them to get some sort of Monte Carlo estimate. And so, yeah, so in summary, when p of x doesn't depend on theta, then we can often estimate this without too much trouble. So now we're going to think about the sort of slightly more complicated case where p of x does depend on theta. And so we're going to now call it p theta of x. And so we're trying to do the sort of the same trick we did before, where we expand out the expectation into an integral. We can again assume we can move the gradient inside the integral. But now we've got a slightly more complicated thing, because now we've got two functions of theta, p theta and h of x and theta. And so when we try to differentiate these with respect to theta, we have to use the product rule of differentiation. And so we get one term where we have p theta times the gradient of h, which is what comes out to be this, exactly what we had before. But we've also got this additional term, like the other term we get from the product rule, where we have grad theta of p theta all times h of x theta. And that is this. And this isn't something we can write as an expectation. So it's now something it's not really obvious how to estimate this. And we would basically like to avoid having to estimate this if we can. So if we go to the next slide, yeah, in summary, it's quite nice to estimate expectations when they do not have a dependence on theta. In this distribution, we take the expectation over. It's a lot nicer than if there is this dependence on theta. And so the reparameterization trick is just a way to rearrange an expectation so that we can take one that looks like this and we can make it look more like this. And so the way we do this is very similar, to remind you of the change of variables rule, in that we're going to take some like base variable, which here we're calling x0. We're going to say this is distributed according to a fixed base distribution u, where u of x0. And then we're going to define some function f, which depends on the parameters theta and also x0. And then it's going to map to x. So we have this x is f theta of x0. And then if we define our base distribution and this function f, like if we define them correctly, then we should get an x here that has the same distribution as the x up here, p theta of x, that we're trying to keep it the same as. And then so if we can do this, we can rewrite our expectation as this. So we take the thing that had the dependence on theta. We now replace that with an expectation over u of x0. So now there's no dependence on theta out here. And then inside here, we just have this h hat, which we have defined to take in x0. And then it uses the parameters theta to turn x0 into x, using this equation. And then it just computes h of x theta. And so it is, yeah. So now we've managed to get the parameters outside of the distribution and take the expectation over. Okay.
Can I ask a question?
Sorry, yeah, go ahead.
Does p theta and u have to have the same support?
Um,
Or does U have to contain P theta support?
yes. So if we want to use the change of variables rule, then this function f theta that's mapping between them should be invertible. So yes, x should be an invertible function of x0. Therefore, they should have not necessarily the same support, but the same number of dimensions. Does that answer your question?
Sort of. I guess.
I think it does. So the question is,
Yeah.
I think you need to restate your questions.
Yeah, my question is, does U and what's the relationship between the support of U and P theta?
So they can have different support. For example, you could have a bounded support between 0 and 1, and then we could define a function f theta that maps from this interval between 0 and 1 to any real number. You could define an invertible function that does that, and so that would be valid. Yeah, basically, I think any sort of pair of supports over for these two distributions is fine as long as we can define an invertible function between them.
Okay, that makes sense.
Okay. Any other questions, or should we move on? Okay, so this is an example of us doing reparameterization. So let's say we have a Gaussian with mean mu and standard deviation sigma, and we want to take an expectation over it, and we want to do the reparameterization trick. So we're just going to sort of there's not necessarily just a single way we can do reparameterization, but we're going to do it in the sort of most commonly done way for a Gaussian. So we're going to define this space distribution U of x0, which is just a unit Gaussian, so mean 0, standard deviation 1. And then we will have the transformation as follows. F theta is mu plus sigma times x0. So these are just the parameters, and is x0. So then to check that this is a sort of reasonable reparameterization, we should make sure that the resulting distribution over x is what we want it to be, this Gaussian. So we can check this with the change of variables rule. So here we just write out the change of variables rule. So we have p theta of x is u of x0 times, this is the term that used to be, or in the change variables rule, in the most general case, this is the determinant of the Jacobian. This is just a sort of one-dimensional example we're looking at. And so the Jacobian is just this 1-by-1 matrix, where this is the only element. And so this element is the determinant of that 1-by-1 matrix. And so basically here we can just plug these terms in, so we can go away and look up what's the probability density for a unit Gaussian, and we get this. We can perform this differentiation on f. So if we differentiate it with respect to x0, then we will just get sigma. And then we do the inverse of the absolute value of sigma, and we get this because we assume that sigma is positive. Yeah, and then so the other thing we need to note is that x0 is the inverse of f from x. And so if we just invert this function, we'll see that we get x0 is x minus mu over sigma. So we can sub this in up here. And essentially what we end up finding is that, yes, this is the probability density function for a Gaussian with mean mu and standard deviation sigma. And so we're happy that this reparameterization is sort of reasonable in that it gives the correct distribution over x. And so now we want to just revisit an assumption we made a couple of slides ago when we were thinking about how we could rearrange, when we were sort of doing this derivation for the, basically for swapping or for moving the gradient symbol inside the expectation. And we just sort of assumed that we could move this gradient inside the integral. And yeah, I don't want to sort of, I think we could go into a lot of detail on like exactly what conditions you can do this in, and I don't want to get too bogged down, but I've just sort of copied from Alex Bouchard's notes. He gives conditions for when this is possible for a scalar parameter theta. And so essentially you have these conditions which essentially say that h hat is a sufficiently nice function. And I think the most interesting condition here is that h hat of x0 and theta has to be differentiable with respect to x0 and theta. And I think what's interesting about this, we will see on the next slide, is it basically tells us something about why reparameterization won't work if we're trying to use discrete variables. So yeah, so I've just copied the second condition over here again. And I want to give this example of what if we're trying to reparameterize a discrete variable. So say we have x sampled from a Bernoulli with parameter theta. So it's going to be 1 with probability theta and 0 with probability 1 minus theta. So one way we could reparameterize this is we could find a base variable x0, which we sample from a uniform distribution between 0 and 1. And then we can define a transformation f, which just maps to 1 if sampled x0 is less than theta, and 0 if x0 is greater than theta. And so this is going to give us the correct probabilities, like x will be 1 with probability theta. But it's not necessarily a good reparameterization because it does not satisfy this condition up here. Basically, f theta of x0 is not differentiable with respect to x0 or with respect to theta. And so this h hat, which sort of contains f theta, is not going to be differentiable with respect to x0 either.
Can I ask a quick question here?
Sure.
Like, I always thought that the reason that you couldn't reparameterize this, discrete variables is, because the sort of reparameterization that you end up with is sort of useless because you can't take derivatives on it. And like, you're also arguing that you can't do this because you're not allowed to swap the derivative in the integral. Am I getting that right? Or?
Correct, yeah.
Okay. So is there like, are they both valid reasons or are they one and the same and I'm just not really
Sorry, can you repeat the first reason you said again?
So here your f of x is defined as the indicator function when, it's sort of like a step function, right?
Yeah.
Which you could do that reparameterization, but your gradient is 0 on one side and it's 0 on the other side, and it's infinite in the middle. So it's kind of useless if you want to do something with it. I always thought that was sort of the reason why this is not a good idea, but there's some, more sort of like math behind it that
I think these might be sort of equivalent reasons, because it's because you have the sort of infinite gradient in the middle of your in the middle of f here, as you say, that is sort of, I think, why we can satisfy that x, when we reparameterize it, still comes from the correct distribution, but why this is not actually, so I think, to answer your question, basically this this is not going to be true, even if you could, even if you just try and persevere.
Okay.
I'm not sure if that. Are there any other questions?
I think they're two sides of the same coin, Baron, basically. But I think your take on what Will is doing is saying that yes, you can't do this swap because but it's you could do this reparameterization, like, you know, computer science math, physicist math, that's a valid reparameterization, but the gradient here is stupid, right? It's like, it does absolutely nothing, right? It's, you know, it's differentiable almost everywhere, and its gradient is 0. What are you going to do with it, right?
Yeah, okay. I think that makes sense. Thanks.
Okay, so I will move on then. And so now we're getting to the start of normalizing flows. And so, yeah, just to define what normalizing flows are, we have, again, like with reparameterization and the change of variables, we're going to have this base distribution. Now we're calling the base distribution P0 instead of U for reasons that will hopefully become clear in a couple of slides. And we will have, again, a learned, well, now it's learned, it's again invertible transformation F theta. And so together, these are going to define a learnable distribution, which we can sample from like this. We sample x0 from the base distribution, and then we transform it using F theta. It also allows us to do probability density computation, just using the change of variables rule. And so since this is a probabilistic programming class, I should say that since we have these sampling and probability density methods, then we can think of a normalizing flow as like this primitive distribution that we can use in our sample and observe statements.
It's worth interrupting here also and saying that this is a nice way of highlighting something that's coming in the next lecture, which is really going to warp everybody's brains, where we're used to thinking about the likelihood of something being something that you can evaluate, right? And this is exactly what Will has said here. The next lecture, when we talk about GANs, are going to be talking about doing inference and modeling in frameworks in which the likelihood is not evaluable, right? So it's just make sure that you get that stuck in your head, that there is a difference between those two things, right? And the idea that that these distributions P theta X are compatible with sample and observe means that you can sample from them and you can evaluate the likelihood, right? And that is not always the case for every distribution, right?
Right. So moving on. So here's just a slide where I'll just mention the sort of main difference between normalizing flows, or the differences between normalizing flows and reparameterization, because they actually kind of look quite similar. Both of them do this change of variables trick where you have the base distribution and the transformation. But I think the main difference is basically in how they're used. Like with reparameterization, we typically have some known distribution with an analytic form that we could just sample from directly if we wanted. But we sort of find it more convenient for estimating these gradients of expectations to just write it out as a sample from a base distribution and then a transformation. Whereas with normalizing flows, we're not trying to approximate some distribution with a sort of known analytic form. We're trying to probably approximate some very complex distribution that we might be learning from data or something. And so we want to just make this very complex parameterized function that's sort of arbitrarily complex, but so that we can still sample and evaluate its log probability density. Yeah, and so now we'll talk a bit about how we actually define this function f theta for normalizing flows. And so the way they do it is using a composition of simpler functions. So we have f theta is just a composition of this series of n functions, which we're going to call f1 theta up to fn theta. And we're also just going to define some notation now to these sort of intermediate variables. So we start with an x0, and then once we pass x0 to f1 theta, we're going to call that x1, and so on. Once we've passed it through the first fi layers, then we call it xi. And finally, after passing it through all n layers, we'll call it xn, or equivalently just x. And so that's the notation we're going to use. Now we're going to think about what does this composition of functions mean for the sort of properties we want this function to have, such as invertibility. And so here we, the slide tells us that as long as each of the individual functions is bijective or invertible, then the composition of all the functions will be. And I think we can sort of see that if we just think about, say we start with an xn, and then we want to invert this to get to x0. Well, we can just sort of invert each function in turn. So we can say xn minus 1 equals the fn of theta, big theta, and theta inverse of xn, and so on until we get down to x0. And so, yeah, as long as each individual function is invertible, so is the composition of functions. Now, another property we want the functions to have is that we can compute their Jacobian for doing the probability density estimation. And so to do this, we can try to use the chain rule of differentiation. And essentially, I'm going to go back to the previous slide just to try to draw this out and give us some intuition for this. But essentially, what we're going to find is that the Jacobian of the composition of functions is just the product of all of the Jacobians of the individual functions. So if I go back to the previous slide, what I've previously drawn. So say we are going to say we just have some sort of simple normalizing flow where we just have a couple of layers. And so we have the x2 equals f2 of x1. We have that x1 equals f1 of x0. And then we want the Jacobian that tells us sort of the Jacobian of f in element, or sorry, row I, column j. This is going to be the derivative of the partial derivative of x2 I, the sort of ith element of x2 by the by x0 j, the jth element of x0. And so another way we could write this is if we use a sort of our total derivative, then we know that these influence each other through x1. So we could say this is the sum over k of partial x2 I by partial x1. That should be 1k times partial x1k by partial x0j. And so let's see if I can move that up a bit. Essentially, this is something that we can get just by doing matrix multiplication of the Jacobians. And so we can end up, I'm just going to sort of write this out, or write this down now. So we can say JF is equal to JF1 dot J. I should have got that the wrong way around. Equal to JF2 dotted with JF1. So, and I think if you sort of stare at this for a while, then it sort of becomes clear that doing this matrix multiplication between these Jacobians is equivalent to doing this sum over k to find each element ij of jf. And so, yeah, I'll not dwell on that for too long. So, yeah, so now let's say we are happy to say that the chain rule, by the chain rule of differentiation, this is the Jacobian of the composition of functions. And then another thing we know from matrix algebra is that the determinant of a product of matrices is just the product of the determinant of each matrix. And so this is, we're just trying to work out how can we efficiently evaluate the determinant of this Jacobian. and then we can plug it into the change of variables rule. So we can say that the probability density of xn is equal to probability density of x0 times the inverse of the absolute value of this determinant, which we can express as the product of the individual determinants. And so essentially, I think the takeaway from this is we can fairly efficiently do the probability density computations just as long as we can evaluate the determinant of the Jacobian for each of the individual layers Fi. And so now we're going to start thinking about the flow architectures, or the functional form of each layer, Fi theta, and what our sort of requirements for them should be, what sort of is a good function to choose. And so we've already gone over that they should be invertible and have continuous derivative. But the other and something to note is that technically they should have a continuous derivative, but this isn't always enforced in practice. Like if the derivative is continuous almost everywhere, then that seems to work fine. So then the other considerations we want to think about is how expressive is the function. Like, yeah, if we want to learn some complex distribution, we're going to need to use either a lot of functions or some very expressive functions in each layer. And then how efficient is it to compute various things, like to run the function or to run the inverse of the function or to compute the determinant of the Jacobian. And which of these we want to be efficient depends a lot on the application that we want to use this normalizing flow for. Like, do we need to sample or not? If we do want to sample, we probably want it to be efficient to compute f in the forward direction. If we don't want to sample, then we won't care about that. And also, like, both computing f inverse and the determinant are likely used for training, for sort of maximizing log probability. So whether or not we want them to be efficient might depend on how much budget we have for training this thing. And so, yeah, essentially there are various considerations, and we're going to look at various different architectures that each satisfy some of these.
Can I ask you a quick question?
Sure, yeah.
Can you tell me a quick application where you would not be interested in sampling at all? There must be some, but I just can't think of one.
That's a good question. I think sometimes essentially just density estimation.
Exactly. I mean, if you just want to do density estimation, if you want to do outlier detection or something like that, you don't give a crap about sampling. You just want to be able to evaluate the probability of something, right?
Okay, yeah, that's fair. That's fair.
Okay, yeah, so we're just going to look through various different sort of choices of function we can use for Fi theta. And so we're going to start off with two sort of simplest and least expressive ones, which are element-wise transformations and affine transformations. And then later on, we'll come to some slightly more complicated and expressive functions that we can use. And yeah, we should remember that when we're talking about different choices for the layers in the flow, like not all of the layers in the flow have to be of the same type. So we can sort of mix and match which of these functions we use in each different layer of the flow, if we like. Yeah, and the other thing I'll say before I start defining all of these layers is we're going to be defining them in terms of the normalizing direction. So this is the direction that takes data, basically takes x and maps it to the normalized distribution, or to x0, basically. This is the sort of normal way that people define these in the literature. So even though we're calling it f inverse, it's sort of what we're going to be writing out when we define these layers. Yeah, so with that, we'll start talking about element-wise flows. So we're going to assume we have some function h, which operates on scalars. And then we just define this f inverse as a function where we take every dimension of our input and apply h to it. And yeah, just very similar to an activation function in a neural network. And the main difference from an activation function in a neural network is that here we need f to be invertible. And so we need each individual h to be invertible. And so we can't use something like a ReLU, but we can use something like a sigmoid, or a common choice is a leaky ReLU. So where we have, instead of being 0 whenever the input is less than 0, then it's just got a slightly smaller slope for x less than 0. Okay, so then I'll move on to affine flows. So yeah, so the previous slide we saw element-wise flows can be thought of as like the activation function in a neural network. This can be thought of as kind of like the linear transformation in a neural network. So similarly, we just have this weight matrix A and a bias vector B. And then the transformation is just multiply x by the weight matrix and add the bias vector. So this is a transformation that we have to be slightly careful here because we need this weight matrix to be invertible. If we want the transformation as a whole to be invertible. But if it is invertible, then we can also work out its determinant, because that's simply the determinant of this weight matrix. Sorry, the Jacobian is the weight matrix, and so the determinant is the determinant of the weight matrix. Something else we have to bear in mind is that if we're using high dimensional, if sort of x is high dimensional, then we're going to be having like fairly big weight matrices, and computing the inverse or computing the determinant takes time proportional to the cube of the number of dimensions in x. So this is sort of fine if x is relatively low dimensionality, but with higher dimensions, then this becomes a bit of a problem. And people do tricks like constraining A to be triangular. And then if it's triangular, it's more efficient to compute the inverse or the determinant. So yeah, so those are affine flows. Yeah, the other thing I should just mention, like the two flows we've covered so far, element-wise and affine flows, they're sort of not ideal. You can't really compute a normalizing flow purely out of affine flows because the whole thing is just going to be a single affine transformation, which is probably not as expressive as you want. And similarly, if you just used element-wise flows, then you're just going to be ending up performing some element-wise transformation, a more complex element-wise transformation on every dimension, which is not really what you want to be doing. So the next few, so yeah, mixing and matching these will improve on that, but we're also going to come to some more complex layers later, which are going to help fix these problems. Yeah, and so I think now is when I'd put in the little pause. So I've just got a recap first. So yes, we've looked at reparameterization, where we use a change of variables rule, and we basically just do this to make it more convenient to estimate the gradient of an expectation. We also have covered normalizing flows, where we do this series of functions, which each can be thought of as a change of variables. And this allows us to model some complex probability distributions. And we've seen a couple of different normalizing flow layers. And later we will look at a couple more expressive normalizing flow layers. So if anyone has any questions, I suggest we take a 5-minute break.
So is it always better to use like flows when you're estimating, say, like posterior, variational posterior in the VE case?
Did you say in the VE case?
Yeah, in for yeah, when you're learning a proposal distribution in the variational inference case.
I would hesitate to say it's always better. It's I think they are a fairly nice kind of variational distribution. Like they're good in that they're very expressive. I think problems you might have would be that they can be more computationally expensive than other sort of variational distributions. So yeah, I think it's a trade-off.
Mm-hmm. And like, how would it work with what is it called, amortization? So like, would you just like have a network that maps your observation into like your base distribution parameters, and then you apply the F from the flow? Or
yeah, definitely something like that. Yeah, like the flows I'm sort of talking about in this talk, they're unconditional, so you can't do this sort of conditional generation or conditional density estimation. But yeah, there's generalizations like that where you can make the parameters of the flow depend on some observation.
Okay.
I think, Greg, you're bringing up a good point that we can talk about before we all take the Emma Hansen Memorial carbohydrate break. Like where do you use these in Prob Prog or in general, right? And I think really you can think of using them in a couple of places. You've identified one obvious one. You have some variational distribution. You want it to be extremely flexible. How can you specify the architecture of such a flexible distribution? You'd like to be able to use it for amortized inference. So indeed, I didn't have Will do conditional flows, but you're 100% right that you could, in the variational inference case, you could make the variational distribution a flow. But that places a very strong inductive bias on whatever that it's like. It's not mean field, but it's something else, right? And it's going the distribution is going to be constrained by whatever the flow family is, right? But another place that you can think about using this is that in all of your languages, you've written primitive distribution types, right? So you've had Gaussian distributions and you've had gamma distributions and that sort of stuff. But also on the model side, it might be the case that you want to specify some distribution, either in a likelihood or as an internal part of a mechanism that you're modeling. And remember, we talked about being able to learn model parameters, right? Well, the flow parameters. So you can either use a pre-trained flow as a primitive, and you can still use it as a sample and observe thing. In other words, something you can observe from. Or you can make the flow parameters be part of the unknown model specification when you're doing model learning as well, right? So you can think of it as being a distribution type that you can stick in where the distribution type itself has learnable parameters, which is kind of cool. Anyway, more questions, or should we take our 5-minute break? Break time. Back at 4:22.
Right.
And we're back with the young but excellent Mr. Will Harvey continuing his guest lecture.
All right. So the next things we look at are the other two types of flow architecture that I'd mentioned earlier, coupling flows and autoregressive flows. So first off with coupling flows. So these are slightly more involved than the previous types of flow we looked at. So essentially the way they work is that they take their input, xi, which is some d-dimensional vector, big D dimensional, and they partition it into two disjoint components. So xia, which has dimension big D minus little d, and xib, which has dimension little d. And then we define some very complex function, which does not need to be invertible, g theta, which maps from basically from xia, component A, to something the size of component B. And so then once we have g theta, we can define these like coupled operations on them, which make up the transformation that we have in one layer of coupling flows. So basically what we do to component A is very simple because we actually don't do anything. We just copy the values from layer I to layer I minus 1. Then we do something slightly more complicated for component B. So we take the values at xib and we add on this complex function of xia, and that gives us our new updated value for component B. And the nice thing about these coupled transformations is that they are efficiently invertible, since, well, it's easy to convert this transformation for A because, again, we don't do anything, we just copy the same value. And then we can invert the transformation we did to part B just by, now instead of adding g theta of component A, we subtract g theta. And so this is a sort of nice way to do the inverse, sort of equally.
Is the index on the x in 31, the last xia, I minus 1a, is that indexing right?
So we could also say xi here, xia, because they're the same.
Okay. They're the same, duh, thank you.
Yeah, and so this is a nice way to sort of define a function that's sort of equally easy to run in inverse as it is to run in the non-inverse direction. Right, and so now we've seen that we can invert it. Now we might ask, how easy is it to compute the Jacobian? So up here, I've just copied the text we had before defining what the transformations are. And now it turns out it actually is very easy to compute the Jacobian because the Jacobian, or the Jacobian determinant, is always 1. And so to see that, I think I will try to write this out a bit, but imagine that we have xi minus 1, and just so let's say the way we partition it, we have xi minus 1a on top and xi minus 1b on the bottom. So then we want to know the Jacobian. And if we just think about it in terms of these blocks, then we think what's so the sort of top left, all the blocks. So the top left is going to be what's the derivative of the sort of component A of the output with respect to component A of the input. And since the output there is just equal to the input, this is just going to be the identity matrix. Then in this block, we're asking what's the sort of derivative or Jacobian of component A of the output with respect to component B of the input. Well, component A of the output doesn't depend on component B, so 0. And then lower down, so for the bottom right, we're asking what's the Jacobian of component B of the output with respect to component B of the input. And here it's just sort of copied over, so it's the identity matrix again. And then now we get to the slightly more interesting block where we have to say what's the Jacobian of component B of the output with respect to component A of the input. And here we actually do now have something we can differentiate and basically take the Jacobian of g theta. And so if we just write that, then we have what we have down below. But a sort of a nice property of the determinant is that when you have this sort of block triangular structure here, then it turns out you can just ignore everything that's not on the diagonal. And so this is the determinant of this is equivalent to just the determinant of the identity matrix, which is just 1. And so we know that with these coupling flows, the determinant of the Jacobian is always going to be 1. So we don't even have to compute.
Does this imply anything about the relative sizes of A and B? I just thought about this for the first time.
No, because so this thing, actually, let me check how I define the dimensions. So A has dimension d minus d. Let's dimension little d. So this thing is going to be a d by d thing. This side is going to be d by d. Then sort of this is d dimensions. This is d dimensions. So it, yeah, I don't think we need to say anything about the
No, it's just me remembering properties of determinants. It's a weird property of determinant that you could make it so that there's only a 0 in the upper right-hand corner, and then the determinant would be 1, right?
Right. I think, yeah, the other thing to remember is these are the identity matrices. So a sort of property I'd missed out is that it's not just that there's like this block is also 0 everywhere except right along the diagonal. There's lots of zeros in here. And so we do actually have, since these are the identity matrices, like zeros everywhere.
Okay, but this comes back to my question of like, does D have to be less than, like little d have to be less than big D over 2?
I don't.
Otherwise, those you can't put identity matrices in these diagonals, right?
I don't see why you couldn't. Yeah, I mean, you can put identity matrices in as long as they're square, right? And they're always going to be square no matter what little d is.
Can I ask another question? Is like,
Sure.
is this like at this point you're not doing anything with all the XAs, right? Like at what point is this still useful? And like, is that a problem?
Yeah, so if we just have one layer of coupling flows, then yeah, we're just leaving lots of the dimensions unchanged. So if we want this to be sort of practically useful, then we're going to have stack lots of layers of coupling flows and swap around which elements we leave unchanged. So change how we partition these into A and B.
So you also have to sort of commute those variables somehow. Is that like, is it, I don't know, it seems like you're sort of playing tricks at that point. Like, is that all fine? Is there anything that, like any complications that arise with that? Or
no, I mean, I think that works fine. People permute them in ways like you can do a random permutation after every layer, or you can just swap back and forth between what you define as A and what you define as B. Yeah, and it is, yeah, it does, I think, feel slightly strange that it works, but it seems to. They make nice images with it.
great.
Shall we move on, or do people want to keep looking at this? I will move on to the next slide then, if that's all right. Yes, and so here, this is essentially just what Berend was asking. If we want to have some sort of expressive function when we compose lots of these coupling flow layers, then we need to group the variables into A and B differently for each layer, just so we don't have the some dimensions of the output being exactly the same as what we had in the input. And yeah, if we're happy to do this sort of switching, how we group the dimensions into A and B, then we can make these, yeah, we can make complex distributions just using coupling layers alone. So unlike with affine or element-wise transformations. And yeah, so this is another extension to coupling flows that is sort of a bit closer to, or this is, I think, generally what people use when they use coupling flows in modern papers. So basically, instead of just doing this addition of g theta to xib, we're going to do some invertible function. So I think this function should be thought of as, it basically has parameters which are given by g theta, and then those parameters define an invertible function on xib. And so, yeah, and so we can still do the inverse because again, we've just copied the component A. And then we can use that to get the sort of parameters to this invertible function. And then we just have to use C inverse to get xbi minus 1 from xib. And so that's, yeah, a slight generalization of coupling flows. All right, so
in that case, the determinant also involves the derivatives of C, right? Like I guess you don't get the identity, you get C primes or something.
Yes, so the Jacobian determinant is going to be a bit more complicated in this case. With, yeah, I guess it's going to have the C primes, and that's going to have some dependence on xia.
Yeah, okay.
Okay, so does anyone else have questions about coupling flows, or shall we move on? We'll move on in that case. So now this is the final type of flow layer. We will look at autoregressive flows. So the idea with autoregressive flows is that we want to do, basically, can we make every dimension, instead of like an element-wise flows where we just make every dimension depend on a previous dimension, or like in coupling flows, there is still a limitation in that some dimensions of the output don't get changed or only depend on some other dimensions of the input. Basically, here in autoregressive flows, we want to make every dimension of the output depend on all previous dimensions of the input. And so the way they do that is as we see in this equation. So first, let me say what this notation means, in case it's not clear. Here we have xi minus 1. So this is the vector x, I minus 1, as in just our transformation after I minus 1 layers. And then we want the jth element of that. And so now we're looking in terms of, we're writing this function out for each individual element of the vector, because we need to define autoregressive flows. Oops, sorry. And so we're going to define the function that gives us each element of this vector as having a dependence on basically this element in the previous layer. So element j, xi, and also, at least in the normalizing direction, is also going to depend on all the previous elements 1 to j minus 1 at layer I. So the thing to note about this is we're looking in the normalizing direction, and we see that each element of xi minus 1 only depends on xi. And so this is a nice property, at least relative to down here. So yeah, first I'll go through what this equation is saying. So this is looking in the other direction. Basically, this is giving us the inverse of this. So if we want to get xij as a function of xi minus 1, then we basically, if we look at just what elements it depends on element j of layer I minus 1, but it also depends on elements 1 to j minus 1 of layer I. So you see, if we're wanting to generate all of the elements of xi, then we have to do them one after the other, because we have to like first compute xi j equals 1, and then when we're computing xi with j equals 2, then this has to depend on xi with j equals 1. And so this is a very slow process when we're running in the sampling direction. And so if we just contrast that to if we're running in the other direction, the normalizing direction, then here we don't have this kind of dependence, because the elements of xi minus 1 just depend on elements of xi. And so we can compute all of these in parallel for every j, whereas here we cannot compute them in parallel, we have to do them sequentially. And so this is a sort of asymmetry in autoregressive flows. They're fast to run in the normalizing direction, but slow to run in the sampling direction. And then, yeah, I never actually mentioned what these functions are, but we have this invertible function C theta and a non-invertible function D theta, or a potentially non-invertible function D theta. So I move on to the next stage. Yeah, here we're just, this is a diagram that maybe can explain that it's in a slightly nicer way. So for the normalizing direction, when we're computing F inverse, we want to compute this output xi minus 1, and we can just do all of this in parallel because each element of xi minus 1, if each of these little blocks represents a dimension of xi minus 1, then each one just depends on some of the dimensions of xi. Whereas if we're going in the other direction, then we take, then for each element of xi we want to compute, it depends both on the corresponding element of xi minus 1, but also on all the previous elements of xi. And that's not really ideal because it means we can't compute all of these elements in parallel. Yeah, so yeah.
I don't think you need to credit Kobazev for that figure anymore.
I should say inspiration from Kobazev. They did not include a hand-drawn figure.
Yeah.
Yeah, so just to summarize autoregressive flows, we've defined something that's fast in the normalizing direction. It's also fast to compute the Jacobian. I don't think I actually mentioned the Jacobian, did I? But it's relatively fast to compute the Jacobian because, again, or the Jacobian determinant, because the Jacobian turns out to be a triangular matrix. And the problem is that if we have it fast into normalizing direction, we have it slow for sampling. An alternative is called inverse autoregressive flows, and essentially this just inverts the function so that now you get it to be slow in the normalizing direction, but fast for sampling. So yeah. Now, yeah, and here we just show some samples from an autoregressive flow, just to put in some kind of picture to see that these normalizing flows can actually model sort of somewhat complex probability distributions, at least as complex as MNIST. And so, yeah, they can generate images. They actually don't look quite as good as the real images, but there we go.
So are you literally trying to model the data distribution here? Are you just taking examples and sort of fitting the normalizing flow? Okay. See Frank nodding.
Sorry?
I asked whether in this image you're literally just, you know, modeling the density of the data distribution with a normalizing flow.
Yeah, I think this image actually I've taken does a class conditional. Well, it says there that it does, but basically.
Mm-hmm. Cool.
Yeah, and so to sort of wrap up the discussion of normalizing flows and maybe make it slightly more concrete, I've got an example of a sort of 3-layer normalizing flow with lots of numbers stuck in. So here is, yeah, so this is like a 3-layer normalizing flow. So the first layer is this affine transformation without the bias term. Then we have this element-wise transformation, which is a leaky ReLU with parameter alpha 0.2. And then we end with another affine transformation with a bias term. So this is, I don't know, I've written out all the numbers. I think it's quite boring to go through it in too much detail, but I'll sort of go over roughly what we're doing. So suppose we're trying to use this normalizing flow to compute the log likelihood of some particular data point. So the data point is x, which is this one, which we could also call x3, and we've observed the values 1.1, 1.2. So then if we're trying to compute the log probability density, we need to run this through the inverse of the flow so that we get the corresponding point in the base distribution. And so we can invert all the transformations as follows. So we start by inverting the final transformation. So we do this by saying we take x3, subtract the bias term, multiplied by the inverse of the weight matrix. We get this number.
Will, your AV connection has paused, so we can see you moving. I can provide the audio for what he's doing if we'd like. Can somebody chat to him and say that?
Blink once with the laser pointer if you can hear us.
Speak and be heard.
Hello.
Again, yes.
Yeah, I've no idea when I sort of disappeared. Zoom is just frozen on my laptop.
Just in the middle of the going through the example.
Okay, well, sorry about that. I will in.
You can just go. You can go with audio on this. That's fine. Just switch back to Notability.
Yeah, will do.
There you go.
Okay, so yeah, we had we observed this data point. Had we? No, sorry, we'd observed this data point, and then we wanted to invert the transformations one after the other. And so we invert the first transformation, subtract the bias, multiply by the inverse of the weight matrix, and get out this x2. And we get x1 by inverting the leaky value. And then we can get x0 by inverting the sort of f1, the first transformation. So then we can get out what x0 is and compute its probability density under a unit Gaussian. And so this is the sort of first step to computing the probability density of x under the change of variables rule. So the other thing we need to compute is the Jacobian. And so we compute the Jacobian just for each of these transformations at the sort of values of x0, x1, and x2. So for like these two are the affine transformations, and we just have the Jacobian of the weight matrix. Here we have the Jacobian of the like element-wise transformation, which is a leaky value, and so is one where the input was positive and 0.2 where the input was negative. And so these are the Jacobians. We multiply them together to get the determinant of the full Jacobian, and basically do this to get the change of variables rule and to get out a final probability density, which is which is a number which we can't really interpret, but now we have it. So yeah, and this is basically the end of the lecture. I've just got this little slide of recap on what types of flow layer we looked at, and the sort of various trade-offs between them. It's like this hasn't been a comprehensive list of all of the types of flow layer that get used, but we've looked at some of them, and at least the coupling layers and autoregressive flows are fairly, I think, widely used. And the affine and element-wise flows are not really very practical if you want an expressive distribution, but they can still be used as building blocks. And yes, so if we just look at them, element-wise flows are sort of very fast to do sort of any operations you want, but not very expressive. Affine flows are fast in the forward direction, but if in high dimensions, they're not so great in other dimensions, and they're not very expressive. Coupling flows are sort of very, they're constructed to be quite fast at sort of any operations, but they're not as expressive as these autoregressive flows. These autoregressive flows are basically very nice and expressive, but they're sort of limited by being slow in at least, or in one of the directions that you would like to run them in. So yeah, it comes to the end. So are there any questions?
On that previous slide, if you were to stack together a bunch of element-wise and affine building blocks like you did in your example, do you actually get something that's good, or is it still kind of limited?
I mean, I would imagine that you can make something that's reasonably expressive if you have like enough of these. It's not something that I'm aware of that people do in practice, so I suspect it's at least like less expressive than the other things you can do with the same amount of computation. But it's certainly this. I can't see why there are any like fundamental limitations to doing something like that.
Like maybe if you do something like that, like you may as well just do the autoregressive flows, or just something that's more powerful anyway from the get-go.
Yeah, I would imagine that's true.
Can I ask a question too?
Yeah, certainly.
Yeah. So from like the practical perspective, when would you use normalizing flows versus like the important sampling methods that we always use?
Those aren't of the same type.
Well, for like density modeling, right? Or like model learning, for example.
Well, but you can't put important sampling on one side of the scale and normalizing flows on the other side of the scale. They're two different things. It's like,
Oh, sorry, I meant like elbow optimization and so on.
So you could do like, again, two different things. You've got one kind of density estimator versus some other kind of density estimator. So you can ask a question about like normalizing flows versus some other way of doing density estimation.
Oh, I see. Yeah, is there like what are normalizing flows practical strengths over other density estimation methods?
So I think a very nice thing about normalizing flows is that you can get the exact probability density computation, and as well as exact sampling. So if you're comparing that to something like a VAE or a GAN, then you can't do this exact density estimation. Yeah, so if you're basically for density estimation, they're very nice in that you can do it exactly, which I think is not the case with an awful lot of other sort of arbitrarily expressive methods.
I see. Yeah, that's quite nice, actually.
It might be worth saying a couple more words about why in the VAE case you can't actually compute the likelihood in case that hasn't landed. You could even just scribble it on the bottom of the slide here, Will. Because of course the likelihood is everybody's favorite word in this course, and evidence, which requires you to integrate over the latent space in order to compute a likelihood, right? If that should be obvious at this point.
Yes, what's this? We want to talk about, computing log p of x, which, if you're doing normalizing flows, you can just directly compute log p of x using the change of variables like we did in that example a few slides ago. If you're using a VAE, for example, then you can only get lower bound on this. So that's great. And you have your encoder, q of z given x. And then you can say this is greater than p of x and z over q of z given x. But yeah, this is potentially not as appetizing as if you can actually compute the exact likelihood. So yeah, log normalizing flows let you get the exact likelihood. Other methods mostly don't. Or like, for example, if they were GANs, then they don't let you get any kind of likelihood.
And again, why do you want likelihoods? Well, there's a project group that wants to be able to compute likelihoods, right? Needs to be able to compute likelihoods. But more to the point, it's density estimates, right? Like surprise, outlier detection.
Can I ask another question?
Yeah, go for it.
Okay, this might be totally impractical and like a really stupid idea, but is there any way to use normalizing flows to actually compute the posterior density by chance?
Do you mean something like approximating the posterior with a normalizing flow?
I think this is very close to what Greg will come in. Feel free to interrupt me at any point. But I think this is actually very close to Greg's question, right? So one situation where you need to be able to compute a likelihood is to evaluate the importance weight in that elbow right there, right? And in general, we've constructed Q in various different ways, but one way you could do it is just to make that whole thing one big normalizing flow, and that would give you a more expressive variational distribution. And if you could drive the KL to 0, right, then you have something that is a perfect posterior distribution, right? I think that more interesting question, a question that I sort of have in my head, not a more interesting question, but a different question is like, what's the difference between having some so we've only talked about density estimation, but we generally speaking, we're doing amortized inference, have been talking about conditional density estimation, right? And when we're doing conditional density estimation, we have the ability to use the conditioning information in a link function that produces, through some deterministic operation, a simple distribution at the final layer that allows you to compute a likelihood, if that makes sense. So here, what this is really about is just density estimation. There's no conditional density estimation. There's nothing in the link function that you can that you can use to build a set of parameters for a simple model at the very final layer, right? But when you have a conditional density estimation task, then there's some question about whether or not this VAE style thing is, or sorry, this normalizing flow style thing is better than simply just using a very complex link function and a very, very simple final, like independent across dimension, normal distribution or something like that. If that makes sense. So comparing those two is complicated, right? You get what I mean, Will?
Yeah.
Yeah. Other questions? This is great, Will. Really
Yeah.
super hyper clear.
Thanks.
And you can't see the faces. Everybody is amazingly excited. Super thankful that you came and gave this lecture. There's so many smiles and like overwhelming, you know, outpouring
as always, I'm sure,
of happiness and emotional support that you know, it's almost making me cry.
Another standard day at the Prob Prog class.
Indeed. So no other questions for Will or me? Okay. Well then, Will, thank you so much. It was really very, very good. And yeah, we'll see you for our final lecture on Tuesday when we start talking about GANs and adversarially learned inference. So see you then. Cheers.